In this video, I want to share with you what is probably one of the most important theoretical ideas that underpin mechanics as we know it, fluid mechanics, solid mechanics, and so on. And it's the idea of a continuum. So what is a continuum? That's the point of this video, trying to get to the bottom of that question. So to answer that question, I've drawn a three-dimensional space here. And I've put lots and lots and lots of dots. And each of those dots represents a molecule of water. Okay? So you can imagine this is like a gas of steam or vapor, water vapor, and it's filling up a space. And everywhere you see a small little dot, that's where there's some water vapor. Okay? So we're going to imagine that everything is uniform inside this space, so there's no gradients of vapor. Everything is relatively still, and the molecules are sort of bouncing around there as they normally would in their state of whatever energy they had. So to understand the idea of a continuum, I want you to look at these two green cubes. So if I were to figure out or estimate the density of water vapor in those cubes, the cubes have a side length for this one is epsilon 2. So if I wanted to figure out the density of particles in that cube, I could add up the number of particles inside the cube. I could multiply by the mass of each particle, and I could divide by the volume of the space, and that would give me the density. Okay? So I can imagine that I'm out here at some value of epsilon equal to epsilon 2. If I wanted to compute the density at that location, I could say, well, density at that location for size box 2 would be equal to the number of particles inside the box. We'll call that N2. We'll multiply by the mass per particle, MP, and we'll divide by the volume, epsilon 2 to the third, and that would give me an estimate of the density inside that box. Okay. So if now I went to another green box of the same size in a different location, and I did the same calculation, I should get the same answer if this distribution of particles is uniform. Okay? So when we're at some large spatial scale, when there's many, many particles inside the box, we can see that it doesn't matter where we put the box. If the distribution of particles is uniform, you can put the box in a different location. The same number of particles will fall inside the box, and so your density will be the same in both cases. And for the sake of a plot, I'll just put that point right here. We'll call that rho 2. Okay, so we have epsilon 2 and rho 2 right here. Now, what if my box got smaller? Now I've got another box here with a size of epsilon 1. Okay? I'll imagine I'm down here. We'll call that epsilon 1. Well, I've drawn this cube in such a way that I've chosen a spot where actually I don't see any dots inside the box. So that means the density at that location is 0. But if I put the box in a slightly different location, I can see a couple of molecules inside the box. So what I'm seeing now is that depending on where I put the box, I might get a different estimate of the density. So now, on my plot here, I might be down here with a density of 0, or I might be up here with some other density. And there's this envelope now where we think the density is uniform. But as we get down to smaller and smaller scales, characterized by moving in this direction, our length scales get smaller and smaller, we could have a density of many different amounts. Okay? So down at the molecular scale, the idea of density breaks down. How do we define density if as mass over volume? If the volume's too small, then we don't have any particles in our box. There's no mass inside our box. We have no density. But if we move the box a little bit, all of a sudden mass shows up. We can't have a situation like that where the existence of important fluid properties depends on where we put our box. So what engineers have done is introduce the idea of a continuum, okay? What we do is, even though in reality, density is not defined at really small scales, we go ahead and say that it's okay to assume that as you get to smaller and smaller scales, that the density remains the same. And so this is known as the continuum assumption. This is the idea that properties of our system, which we're going to model mathematically, exist at a point in space, even though as we move to a single point in space, those properties actually break down. So that's the continuum idea, is that we can go down to a point, and when we're at the scale of a point, fluid properties like velocity, density, and so on still exist. Okay, so this idea of a continuum is needed in order for us to study the movement of fluids and the mechanics of fluids mathematically. So what I've written here is a differential equation describing mass conservation of a gas. It's called the Euler equation. And what it says is that the change with respect to time of the density of the fluid plus the dot product of the fluid velocity times the gradient in the density plus the gradient times the divergence of the velocity is equal to 0. So this equation cannot be solved unless rho is a differentiable function. So rho has to be something that smoothly varies in space and time in order for us to be able to compute derivatives of rho with respect to time and derivatives of rho with respect to space. If we have a situation where rho can go to 0 or go to 1, and you can have gaps in rho, then it's a non-differentiable function, and that creates problems for our mathematical modeling. So bottom line is that this idea of a continuum was introduced so that we can model fluid properties at the scale of a point. And the scale of a point is where derivatives exist when we need to sort of use the fundamental theorem of calculus. So that is a basic idea that goes into all of mechanics. It's used in fluid mechanics, solid mechanics, and other areas. And I didn't think the textbook did it justice, so I wanted to give you a little introduction.